Assalamu alaikum. It's our 10th lecture of Advanced Electromagnetic Field and Waves, and in this lecture we will going to solve again numerical number 7.2, which we discussed in problem in lecture number 9. Okay, so in lecture number 10 we will briefly discuss the same problem because this problem is very important and very conceptual to learn the basics for the advanced electromagnetic field and waves. Okay, so for that we are going to do the same thing as we did in lecture number 9, but in this lecture we'll go through briefly. Okay, so let's start with this lecture. So as you know that we have three regions. Like here we have our region 1, you can say N1. Here you have region 2, you can say N2, and here is the region 3 is the N3. Okay, where N is the reflective index of the medium, you can say region 1. This is region 1 and this is region 2, you can denote it by R2, and this is region 3, you can denote it by R3. Okay, so for that first of all you have to set your coordinates. So let's assume we are taking this direction. Okay, z is in this direction, x is in this direction. So this is the coordinates which you have to initialize before solving this problem. Okay, so what we have is we have an electric field. A wave is coming, it have to strike with this boundary. Okay, and here you can say, let me write here again this thing as, so here are the boundary conditions. Here is the boundary condition z equals to 0, and here is the boundary z equals to d, and you know that the separation between two is also d. Okay, yes, so a wave is coming. Okay, so here is an electric wave. A wave is coming, which is an electric field in this direction. You can say, because this is initial, so you can say EI. Okay, similarly your wave propagation is in this direction, means this is in z direction, because you see that uh, wave propagation in this, and here is the z, so you can say your wave propagation is in the z direction, whereas your electric field is in the x direction. Okay, because we initialize these coordinates, so you can say ki. Okay, because this is for first region, so you can say 1 here, and you can also write 1 here. Okay, because you are in region 1. This is region 1, this is region 2, and this is region 3. Okay, if your case direction is this and electric field is you, what how you can find the direction of magnetic field? As I told you in previous lecture, you have to align your fingers in the direction of electric field. So this is in the direction of electric field, your thumb must be in the direction of wave propagation. Okay, so you can see, yes, I am right, my thumb is in the direction of k, as you see, and my fingers is in the direction of electric field. What you have to do, you just have to curl your fingers. So I curl my fingers. So curling my fingers denotes the direction of the magnetic field B. So magnetic field is out of the page. Okay, for the out of the page we will denote it by dot sign. Okay, so this is the direction of magnetic field. Is in the y direction. Why y direction? Because you see that your wave propagation is in the z direction, your electric field in the x direction, so h means magnetic field must be into the y direction. Why? Because you know that electric field, magnetic field, and wave propagation are always perpendicular to each other. This is definitely in y direction, but how you know that this is positive y or negative y? This I told you by this rule. If this is out of the page, so this is positive y. If this is into, then this is negative y. In this scenario, this is out of the page. Okay, so means this is positive y directions, your magnetic field. So what happens, your this electric field, this wave strikes with this boundary. After striking, it will, okay, reflect back. So when it reflect back, you can see only wave propagation direction changes. Okay, so you can, now this is initial, so this is r reflected. Again you are in first medium, so that's why you can write 1, but the direction of electric field not changes. This is er now for reflected back. Again you are in one region, so e1. But how you can find but you can see now your wave propagation is in the negative z direction, but your electric field same in the positive x direction, but definitely your magnetic field is in the y direction. But how you can find either it is positive y or negative y? Same procedure, you have to align your fingers in the direction of electric field, and your thumb in the direction of k. Now your k is not here, your k is, you can see, in this direction. So how you can, so you can use this. Okay, so you can see my electric field lines align my fingers, and my thumb aligns my k value. So what you have to do, you have to curl your fingers. So I curl my fingers, so you can see the direction of magnetic field is into the page. Now not outward, now it is inward. For the case of inward, we use this cross sign. Okay, and this cross sign means into the page, means negative direction. Okay, negative y direction. So some of the wave is reflected back after striking this boundary, but some of the wave transmitted into the second region, which has reflective index n2. So you can see, let me draw for second region, okay, below. Okay, so some of the wave goes into the second region. Again, it has now k2 because you are in second medium. K2 and the direction of electric field same. It becomes E 2, okay, because it is going, so it is E2 plus, okay, and this is K2. Similar, by this rule, your magnetic field is out of means positive, so it is dot. So your H 2 plus, 2 means you are in second region, and plus means it is going wave. If your wave is reverse back, then we should write by negative sign. After going in this boundary, in this region, some of the wave again reflect from this boundary. You can see the second boundary, this boundary. Once your wave is in the second region, then it have must strike with this boundary. Okay, after striking with this boundary, some of the wave again reflects back into the second medium. So what if again reflects back? Yes, you can see again the direction of wave propagation changes because you are in second medium, so it is k2. In initial case, it's k2. In the positive z direction, only the direction of wave propagation changes. Now it's in the negative z direction, but the electric field is same now because it is reversing. It's reverse wave, so we can use e2 minus. Minus is for reverse wave. Okay, so this is but now in this case, how you can find the again you can find the magnetic field by this rule. Align fingers in the direction of electric field, your thumb is in the direction of k. Curl your fingers, your curling fingers denote the direction of magnetic field. Now your magnetic field is into the page. So for the case of into, we use cross sign, and cross sign means negative y direction. Okay, now you are in region 2. As I told you, some of the wave strikes with this boundary, okay, reflects back, this scenario. And after striking this boundary, this is possibility that some of the wave again transmitted into the third medium. Okay, so for the case of third medium, I draw my figure here. Now your electric field is in the third medium. So again, your wave propagation is in the z direction. Now it's become k3. Why k3? Because now you are in the third region. Okay, your electric field direction is same, e3 plus, because this is going wave. For the case of going wave, we use a plus sign. Okay, now by this rule, again your magnetic field is out of the page. For the case of out of, we use dot, and means positive y direction. Okay, e3 plus. There is no boundary. Okay, after this, so if there is no boundary, means there is no reflection back from this. Okay, so this is the illustration of the diagram. Now what we have to do, we have to make the electric field and magnetic field wave equations for the scenarios. Okay, so let us first do for region 1. Okay, for region 1, what is the direction of electric field, we can use E1. Okay, because we are in the first region. Okay, you can see in first medium we have two waves, the incident wave and the reflected wave. So how you can write their wave equations? Like, you can see electric field in incident is in the x direction, so you can see x. Okay, now you have to write amplitude. So for the case of amplitude is E naught. Okay, because incident, so E naught I. Now you have to write e power iota k1z minus iota omega t. So this is your wave of the incident. Because you know that e power iota kg minus iota omega t, whereas yk1, why? Because you are in the first region, you are in first region, that's why you have to use k1 here. And yz here, because you know that your wave propagation k is into the z direction. Okay, you see z direction, that's why z. And y positive because it's in the positive z direction. And plus, because there is also reflecting back region wave in the region 1, so we have to also write this. Again, your electric field in the positive x direction, so again x cap. Okay, again x cap. And now you have to write the amplitude, you know that E node, and you can write it by R, because this is the reflected back region. Okay, and again e power, now minus iota k1z. Why minus iota? You can see that now the direction of reflected wave propagation k is opposite to k. This is the direction of z, but you can see in this, this is in the negative z direction. Okay, but electric field in positive x, that's why already positive x. But here initial positive z direction, that's why positive z here. But in reflected case, it is in the negative z direction, that's why we have to initialize minus k1z minus iota omega t as it is. Okay, so this is the equation of electric field, okay, in region 1. Now what we have to do, we have to write the magnetic field equation. How we can write h1? Basically, you know that, as I told you, in this scenario your direction of magnetic field is out of the page. For the case of output, out of, this is positive direction, and this is k is in the z direction, electric field in the x. So magnetic field h definitely is in the y direction, and it's in the positive y direction. Now you have to write the amplitude, because you know that one thing is that, you know that h naught is equals to, okay, e naught divided by z naught. Here is h naught for the amplitude of h, but we have to replace h naught by E1 divided by Z1, because you are in the first medium. Okay, because this is going wave. We can also write plus here. For the case of going, this is back, so we can write minus here. Again, this is going, we can write plus here. And e power, the again in this scenario, the direction of k is in the positive, so e power iota k1z minus iota omega t. Similarly, in this case, in reflection back case, in reflection back, the magnetic field is in the y direction, but it's positive y direction, because I told you this is the electric field and this is the k. And you have to curl your finger. Now you have into the page. For the case of into the page, okay, so you have negative direction, because magnetic field is in y, so it is minus y direction. Okay, minus. For the case of reflecting back, again magnitude is now e1 minus y minus, because this is reflection back wave. Okay, divided by z1, because you are in the first medium. Okay, e power minus iota k1z. Again, in this, you know that your direction of wave propagation k is in the negative z direction, that's why we have to write minus iota k1z. Okay, minus iota omega t as it is. So this is the equation of electric and magnetic field, okay, in region 1. Now you have to do the same procedure for region region 2. Okay, for region 2, again you have to write first of all the electric field. So electric field equation now becomes E2. Okay, because now you are in the second region. E2 becomes in second region. These are the diagrams. Okay, these are two diagrams which we have to concern. In second region, you know that electric field is in the same x direction, positive x, so x cap. And the magnitude of electric field, you know that E naught, and because this is going wave is always denoted by plus sign. Okay, and e power iota k2z. First of all, why k2? Because you know that now you are in region 2, you have to use k2, and you know that the k2 is along with the direction of z, means positive z. That's why positive iota k2z. Okay, minus iota omega t as it is. Now for the case of reflecting back wave concern, okay, what we have to do, again you can see electric field in the positive x direction, so again plus x cap means positive direction. Now amplitude, you know, na e naught and minus y minus because it's the reflecting back wave. Okay, and again e power minus iota k2z. Why minus k2? Because you know that we are in second medium, that's why k2. And you know that you see that k2 direction is the opposite of the z direction, so that's why we have to use minus z. Okay, so minus k2z minus iota omega t as it is. So this is your equation, okay, of electric field in the second medium. Now what you have to do, you have to write the equation for the case of magnetic field, means b2, sorry, h2. Okay, so same procedure in this scenario. You know that you can align your fingers and thumb out of the page. For the case of output, definitely your like magnetic field is in the y direction, but for the case of output this is positive y, so y cap. Again amplitude is denoted by h naught, but we have to use h naught is equals to e naught by z naught, so e naught plus divided by z2. Why z2? Because now you are in this second medium. Okay, and e power iota k2 z minus iota omega t as it is. Okay, now for the case of this, you can write h2 minus. In this scenario you can see that electric field this k direction, thumb is this, curling fingers, so curling fingers denote this is into the page. For the case of into, we have to use minus. We know that magnetic field is in the y direction, this is negative y direction. Okay, so again magnitude is e naught minus y minus because this is reflecting back wave, divided by z2 e power minus iota k2z. Why minus iota? You can see again k2 is in the negative of the z direction, minus iota omega t as it is. So these are the equations of electric and magnetic field in region 1 and 2. Okay, now what we have to do, we have to do the same procedure and write the equation for the region 3. Okay, so how you can write the equations? So let me write here region 3. Okay, for the case of region 3, first of all, this is the diagram of region 3. Because there is only transmitting medium, there is no reflection back because there is no boundary further. So let's start. Okay, this equals to, again you know that electric field direction is again in the x direction, so x. Now the amplitude, you know that e naught 3 plus y3 because you are in the third medium, and y plus because this is going wave. Okay, and e power iota k3z. Okay, why k3? Because you are in the third medium, and you the direction of k3 is along the direction of z, that's why positive minus iota omega t as it is. Because there is no reverse back medium, so there is 0, so this is final result for the case of electric field in region 3. Similarly, for the case of magnetic field in region 3 can be written as, first of all, you know that in this magnetic field, you know that thumb, this electric field is out of the page. For the case of output, we have to use positive y direction, and amplitude, you know that written by this, so e naught 3 plus divided by z3. Why z3? Because you are in the third medium. E power, okay, you can write minus iota k3, sorry, plus iota k3 z, because you know that the k3 direction is along the direction of, okay, that's why iota k3 z minus iota omega 3, because there is no reversing back. So that's all. So that's all the three region equations of electric and magnetic field, okay, for your concern. Now here what you have to do, you have to apply the boundary conditions. Okay, here you know that there are two boundary conditions at z equals to 0, at z equals to d. Okay, these are the two boundary conditions you have to apply. So let's apply the boundary conditions. So first of all, let's apply the boundary condition z is equals to 0 in region 1 and 2. Okay, because you know that in region 1 and 2 the boundary is z equals to 0, in region 2 and 3 the boundary is z equals to d. So for first of all, let's solve the boundary condition at z equals to 0. So let's apply boundary condition at z equals to 0 in region 1 and 2, as I told you. Okay, so region 1 and 2, let's apply for the electric field, because you know that uh, electric field components, okay, tangential components of electric field are continuous, or you can say equal. So this is the first boundary condition we can use. And you also know that the tangential components of okay, magnetic field means H is are also continuous. So we can also apply this boundary condition. So these are the two boundary conditions. So let's apply first boundary condition in region 1 and 2. So what we have to do, we only have to use z equals to 0. Z equals to 0. So where is z? You can see in the case of electric field here, e power z, okay, iota kz here, kz. Similarly in region 2, e power here iota k2z, and here minus iota k2z. So there here are the z. What we have to do is only have to put 0 here. So when we put 0, 0 multiplied by iota k1, 0 multiplied by iota k1 becomes 0, means e power 0. Here again e power 0, e power 0, and you know that e power 0 basically equals to 1. Okay, so you will only left with e power, okay, e power 0 becomes 1, and you will only left with e power minus iota omega t. Here also e power minus iota omega t, here also e power minus iota omega t, here e power iota omega t. You will left with, what you have to do, you just have to take common. Okay, so how you can write, so you can write, first of all, put z equals to 0 in this equation. After putting, you will get, you will left with, okay, e naught 1 plus e power minus iota omega t plus e naught 1 minus e power minus iota omega t. This is for the case of first, because you know that tangential compare e1t equals to e2t. This is for e1t becomes equals to e2. So e naught 2 plus e power minus iota omega t. Okay, similarly e naught 2 minus e power minus iota omega t. What you have to do, you have to, because you know that here e power 0 becomes 1, you will only left with e power minus iota omega t. Okay, and taking x common from this, from region 1, and taking x common from region 2, they will cancel out. That's why I can't write. Okay, so you can also take common from e power minus iota omega t from this. You can also take common from e power minus iota omega t from this, and cancel each other. So you will only left off with e plus e naught 1 minus equals to e naught 2 plus e 2 minus naught. Okay, so this is your final equation for the case of, okay, while applying boundary condition. So you can name as this equation a. Now what you have to do, you have to apply the same boundary condition in the magnetic field, because you know that magnetic field, the tangential components of magnetic field H are also continuous, also equal. So what you have to do, again you have to put Z equals to 0 in magnetic field equation for region 1. Again you have to put the Z equals to 0, okay, in magnetic field in region 2, and because the tangential components are equal now, but then what you have to do, you have to equal h1 h2, okay. So after doing this, again you can see why direction is common, so you should take common, and also by taking common cancel each other, you will only left with this. Again e power uh, z, when z is equal e power 0 and minus iota omega t, you will only left with e power minus iota omega t. Similarly e power minus iota omega t here, taking common e power minus iota omega t from this equation, and again from this equation e power minus iota omega t take common, because you know that e power where there is z, so e power 0 becomes 1, so you will only left with e power minus iota omega t here, here, taking common from these two, taking common from these two, cancel each other, and you will only left with I should write here the equation for the case of magnetic field. It becomes e naught 1 plus divided by z1 minus e naught 1 minus divided by z1 becomes equals to, because tangential components of magnetic fields are equal, so e naught 2 plus divided by z2 minus e naught 2 minus divided by z2, okay. So this is only you will left for, as you can see, as e1 plus divided by z1, okay, minus e1 minus divided by z1, okay, because y taking common and e power minus iota omega t taking common cancels with taking common from region 2 also, okay. So you will only left with this equation, so you can say this equation as equation B. Now what you have to do, you have to apply the second boundary condition, okay. What is the second boundary condition? Second boundary condition, as I told you, you have to you know that when I draw this figure, you know that this is our first region, and in first and second region there is a boundary at z equals to 0. So here we find the equations at z equals to 0 boundary condition, and now the second boundary condition is the z equals to d, because you know that the distance between two boundaries are d. Now there is this boundary at z equals to d. Now you have to find the equations at boundary condition at z equals to d. So let's find. Another thing you have to keep remember this, when you are in region 3, you crosses distance, okay, because you know that this is at z equals to 0, and this is distance is d, this distance between two boundary is d, okay. So when you are in region 3, now what is the net distance is basically this is total z, and you will okay, you will move forward from d, so it becomes z minus d. So now the distance is z minus d, okay, when you are in region 3. So as you know that these are your equations of electric and magnetic field in region 3. So these equations can be rewritten as, let me write here, only the thing changes is here z replaces by z minus d. So let me replace here, okay. So it becomes z minus d minus iota omega t as it is. Again this z changes into z minus d, okay, z minus d minus iota omega t as it is. Why this happens? Because you know that when you are in the first and second region, means you are in the first boundary conditions, you know that the distance is z equals to 0, and this complete distance is z, and the distance between two boundaries d. So when you are in region 3, you already covered this d distance, and total distance is z. So when you are region 3, so the distance in region 3 becomes z minus d, okay. That's why we have to only change this distance, okay, z minus d. Now what you have to do, you have to apply the boundary conditions, and you know the boundary condition is z equals to d. What you have to do, you have to put z equals to d in these equations. Now what you can see here, first of all, you know that z equals to d boundary condition you must have to apply in region 2 and 3, not 1. Not now 1 is not concerned with this boundary condition. Yeah, so this boundary condition is only apply in region 2 and 3. Okay. Okay. And you have to equal, because you know that the tangential components of an electric field E and magnetic field H are equal in. Okay, so equals, that's why we have to apply this boundary condition. And second, for the case of second region, your equations remains same, okay, as we wrote here. Okay, and in region 1 the equation remains same, but only changes in the region 3. Why? Because you crosses the distance d, and now you are in the z minus d distance. That's why the you only changes with this. Now what you have to do, you have to apply the first boundary condition, which is this. You know that tangential components of electric fields are equal. So what you have to do, you have to put z equals to d in electric field equation, equals to second region, means other region. In this scenario the third region is the other region. You have to put z equals to d here also. So let's first put z equals to d here also, taking x common from this region 2, and taking x, there is only one x, so x cancels with this x, so we will not writing here also. Okay, and e, so we can write it, or you will only left with e naught plus, okay, e naught 2 plus, because you are taking from second region, because we have to apply this boundary condition z equals to d in region 2 and 3. Okay, so this becomes e power iota k2, e power iota k2 d. Why d? Because we are z equals to d, so this z equals to d. And as you can see, taking e power minus iota omega t from this, and now again for this concern, so it becomes, okay, plus e naught 2 minus, okay, then what you have to write here, e power, again this becomes minus iota k2d. Okay, why we are not writing e power minus iota omega t? Take common e power minus iota omega t from this and this. We will cancel that with this. Okay, you can see e power minus iota omega t here also. So e power minus iota omega t cancels with taking common from this. Okay, that's why I'm not writing. So you have to equal tangential component for first equals to second other region, and other region is this. So x cancels with this already, and we will only left with e naught 3 plus, okay, e naught 3 plus. And you have to put z equals to d here, because z equals to d boundary condition, so that when z equals to d, d minus d 0, and e power 0 1, so you will only left with e power minus iota omega t. So e power minus iota omega t cancels with this. Okay, so you will only left with this equation. Okay, now what you have to do, you have to find the magnetic field, okay, for this boundary condition as z equals to d. So how you can find, again you have, what you have to do, you have to put z equals to d in this equation, and in this equation too also. Okay, so after putting in this equation, first of all take this y cap common from this equation, and y cap from this region cancels each other. Okay, and when you put z equals to d, so this becomes 0. Okay, and you will only left with, okay, e power minus iota omega t, and taking common from e power minus iota omega t from this cancels each other. Okay, so how you can write, so this equation becomes e naught 2 plus divided by Z2 this. Okay, because you are in the second region, that's why 2 plus. Okay. mm, E power this, e power iota k to d, because z equals to d. So e power iota k to d. Similarly plus, sorry, minus here. Okay, because you can see minus here, so we can use minus here. Okay, minus this. Okay, e naught. Okay, it becomes 2 minus divided by z2. Okay, e power again minus iota k to d, e power minus iota k to d. Okay, you can see here z equals to d, z minus iota k to d. Here you must have to equal this with your second region, and second region electromagnetic field is this. It becomes e naught 3 plus divided by z3. And you know that when put z equals to d here, so d minus d becomes 0, e power 0 only 1, and you will only left with e power minus iota omega t. And here also e power minus iota omega t, e power minus iota omega t. Take common e power minus iota omega t from region 2, cancel that e power minus iota omega t with region 3, so you will only left with this equation. So these are the equations after applying the second boundary condition. So that's all for today's lecture number 10 of advanced electromagnetic field and waves. So here are the notes, neat notes. You can take screenshot and do neat work on your copies. Okay, so that's all for lecture number 10 of advanced electromagnetic field and waves. We will upload more videos for this course. Okay, so thanks for watching. Stay tuned with us. Allah Hafiz.